Good morning to all. My warm welcome to the authorities and the guests to this academic conference, as well as welcome to students. This is a very important event. And now I'm going to switch over, even though my English isn't that good. I've been asked to give this presentation in English.
It is for me a really great honor to do this presentation of Professor Bruce Alberts, who is a prominent biochemist and molecular biologist who, together with other scientists, created a textbook, and I will start by that is an absolute key piece for all the students in biochemistry and molecular biology, the molecular biology of the cell, a textbook that is now in its sixth edition, and that for all of us is simply known as the Alberts. So, Professor Alberts was president for 2 6-year periods of the National Academy of Sciences of the United States. And during his period at the Academy, he was instrumental in developing the landmark National Science Education Standards. In his words, and I'm going to read his statement, the type of science as inquiry is very important. And he emphasizes that this type of science as inquiry emphasizes logical, hands-on problem solving, and it insists on having evidence for claims that can be confirmed by others. It requires work in cooperative groups where those with different types of talents can discover them, developing self-confidence and an ability to communicate effectively with others. After completing in 2005 his 2 terms as president of the National Academy, Professor Alberts returned to the University of California at San Francisco, where he has a position of Chancellor's Leadership Chair in Biochemistry and Biophysics for Science and Education. He was also editor-in-chief of Science in the period 2008-2013. In 2009, in the period 2009-2011, he was appointed by President Obama as Science Envoy, one of 3 Science Envoys. And in 2014, President Obama awarded him the National Medal of Science. I would also like to emphasize that in addition to his eminent preoccupation with science education, Professor Alberts has been a very strong supporter of women in science. And as a woman scientist, I really recognize his preoccupation for the fact that it's not always so easy for women scientists to fully develop their potentials. And to conclude, I would like to read a statement that he made that the creativity, openness, and tolerance that are inherent to science, he believes that scientists all around the world must now band together to help create more rational, scientifically based societies that find dogmatism intolerable. Thank you, Professor Alberts, for being here with us, and I invite you to give your lecture.
Good morning. It's a real pleasure to be here back in Chile. I think this is my 5th visit, especially to participate in a meeting organized by Jorge Allende, not only a friend, but a great champion of science education around the world. As you heard from Yuli Chong, he was the first chair organizing all the academies of the world to work together on children's science education. And this program remains one of the most effective important programs of the International Association of Academies. So my title today was given to me by Jorge. He made it up. The point is, and my bottom line will be, that we are not going to make major progress in science education unless many more scientists pay attention to the issues that this conference is addressing. The energy, the effort that it demands from teachers requires that the teachers and the school systems and the states in countries that promote science education for children have scientists continually helping to support the teachers and support the system. It otherwise will not work. So this is the central lesson for my 12 years in Washington, D.C. as president of our academy. To be president of the United S Academy is a full-time job, so I had to close my laboratory. And basically, this 12 years was a great education for me in what science can do for the world. And so my basic observation was that science teachers and scientists must achieve a much higher degree of influence throughout both their nations and the world, and this is very important for the future of the world. As was said, I mean, you could look around the world with all this misunderstandings and dogmatism, and the scientific spirit is critical to all democracies. I first learned about the word scientific temper my first year as president of the academy when I went to India. I learned about the first prime minister of India, Prime Minister Nehru, stressing the importance of science for his country because he recognized that the creativity, rationality, openness, and tolerance that are inherent to science are critical for any society to be effective, especially diverse societies like India with 50 different languages, 50 different major languages. Okay, so this is the image we want for science. This is a statue of Einstein in the front yard of the Academy in Washington, D.C. My office was right behind the statue. And this wonderful statue of Einstein has a very big lap. And he's very approachable. And the students who come to visit Washington for a week with their schools almost always end up taking their picture on Einstein's lap. This is not the image we have for science, either in the United States or most countries. Most adults and children think science is something too hard for them or too strange or not really important for them and their country. This is the image we need to change, and the only way to change that is through science education. So a critical problem we need to solve is that it's very easy to teach science poorly, but it's much harder to teach science well. And adults in many countries, including the United States, have incorrectly defined what the word science education means for most students. And I'm going to give you a true story. I gave a talk at a major university in the United States, and a mother came and told me this story very recently. A third grade student, who's a very young student, comes home from school and tells his mother, "Now I get it. Science is just like spelling. You just need to memorize it, and it doesn't make any sense." This is such a sad statement, because all those the wonders of science, and you know, it's nothing to do with science, memorizing all these science words. But this is what it's easy to teach. And this is an example of what I mean. As was said, my field is cell biology. I think the cell is the most amazing thing in the universe. It's a tiny little chemical system that can self-replicate, and then an egg could make a human being. It's amazing. But we make it terribly boring. This is what I'm going to give you an example from a U.S. textbook, okay? I call it Science Education is Mentioning. They feel that all the students, these are 12-year-old students, have to know all the words about cells. So they have all these bold words. Here's an example. Running through the cell is a network of flat channels called the endoplasmic reticulum. I had never heard of the endoplasmic reticulum until I was a scientist. But now every 12th grader has to memorize this is, and it says, this organelle manufactures, stores, and transports materials. And then the next sentence is a similar sentence with another bold word. In this case, it was the Golgi apparatus. It goes on like this for the whole 800-page book about science, life science. And then there's a chapter self-test just to make sure that you understood what was important. It says, write a sentence that uses the term endoplasmic reticulum correctly. They only have one sentence, so they have to memorize this sentence. Here, they're supposed to memorize this sentence, and that's learning science. So that's why that student came home and said, science is just like spelling. You have to memorize it, and it doesn't make any sense. This sentence means nothing to somebody who really doesn't understand the cell. Okay, so our tests define what we mean by science education. It's much easier to test for science facts than to test for science understanding and abilities. And poor tests, and we have many of them in the United States, force the trivialization of science education and drive most students, including many potential scientists, away from science. It also causes all our politicians, or most of them, to hate science, because what they remember about science is this horrible torture of memorizing the endoplasmic reticulum. So a major challenge is to produce good tests for science. A good test will motivate good teaching and learning, and this is a very important and difficult task. So this is what science should look like in school. This is a picture of 12-year-old students in San Francisco. You can't see it, but in the back there's a teacher walking around a noisy classroom, and the students are trying to solve appropriate problems working in groups. So any classroom that's quiet, where the teacher's in front of the class just talking, that is not a science class. So here's a quote from Wynne Harden, who's one of the pioneers in this field of modern science education, and she's here in the audience somewhere. I can see her. Anyway, 1995 she wrote, "In practice, ideas which are not related to previous experience and thinking are of very little use to us. They do not arise from past experience, and so are not called forth when past experience is used to explain new experience. Such ideas have to be committed to memory by rote, like endoplasmic reticulum, right? And are usually usable only in contexts close to those in which they were learned. Understanding, which by definition is applicable, is created by development and change in ideas." And that's what those students were doing in the classroom. And here's an example of what the curriculum, part of the curriculum for the first year of school was in San Francisco in 1993 when I left. At the right time of year when there's seeds on the ground, the children were given white socks and told to walk out underneath the trees and come back and take the socks off and pick off all the specks, the black specks on their white socks. And they put them, each speck in a different numbered square. And their job was to figure out which specks were seeds and which specks were dirt. And the way a good teacher has to teach this is to wait for some child to suggest an answer, not to tell them the answers. And they start by looking at each speck with a magnifying glass or a tiny little microscope, plastic microscope, and they draw a picture on another piece of paper of each of the specks, and then they have this discussion, and eventually Some 5-year-old student says, I think the regular shaped objects may be the seeds. Okay. And the teacher doesn't say that's correct. Teacher says, what does the class think about it? And then, the wait till the class says, well, that's a possible idea. Now, why do seeds stick to socks? Because seeds evolved to stick to animal fur. That's how they were transferred. So many seeds are sticky and stick to socks, but a lot of the other stuff, rocks and dirt, stick to socks too. So most objects will not be seeds. And then they have a discussion about how would you test this idea? And eventually some kid will come up with a brilliant idea. We could plant both the regular shaped ones and the non-regular shaped ones and see if we only get plants growing from the regular shaped objects, which we thought were seeds. And again, the teacher doesn't say this is correct. The teacher says, ask the class whether they think that's a good idea. These are 5-year-old children. Eventually the class, says, yes, we could do this, and they do the experiment, of course. Anyway, this takes time. So the vision is to have a science education that includes solving hundreds of such challenges over the course of schooling that leads to high school graduation. I believe that children who are prepared for life in this day would be great problem solvers in the workplace. Companies need people who could think and solve problems. And the economy needs those people to be successful. There are also people who are able to make wise judgments for their family, their community, and their nation. Everybody's always trying to get your money by fooling you, or they're trying to get your vote by fooling you. And finally, there'll be adults who reject what I call magical thinking. We have lots of magical thinking in this world which can get us in real trouble. We need people who use evidence and logic for making decisions. So now this is something my colleagues in the United States don't like. Because when I got to the Academy in 1993, I took the job, I was offered the job because they said I could use the Academy to help work on science education. And many of my members of my Academy, we have 2,000 members of the U.S. Academy, said that this is an important problem, but it has nothing to do with us scientists. It has to do with those people who write textbooks, it has to do with teachers, it has to do with everybody else but us. But in fact, I realized in part of my education in Washington, the rate limiting step, the most important change we could make as scientists to change lower level science teaching is to change what we do at college. An important barrier to redefining what we mean by science education starts at college, and the traditional lecture format that allows a single professor to have a room full of 500 students and talk about science. That's the way we generally teach science. We need to have much better alternatives that are not much more expensive, and this is actually possible. Many experiments are being done, and I'm going to talk about them. So the responsibility of scientists is to first start by changing how they teach their own science courses. So this is a wonderful example at the University of Minnesota where they built a new building for science and education, which has 16 flat classrooms. These classrooms have round desks that seat 9 people and 2 laptops connected to the internet. And the woman with the star on her back is the Dean of Biological Sciences, Robin Wright, who was one of the major forces for changing the way they taught science at the University of Minnesota. And here's active learning in college biology class. It looks just like that 12-year-old class. The students are given material to read and videos to watch, and they have a very short 5-minute exam to make sure they did the reading before they start. But they spend the whole hour-and-a-half class period trying to solve problems using the internet as necessary. And there's been a lot of research, scientific research done on how students learn in college with active learning as against standard lecture. And this is a publication that compiled the results from something like 260 studies of college science teaching in all different disciplines. And they showed that even mild forms of active learning have major effects in student performance, greatly improving the fraction of students who pass the course and who understand science. So as scientists, we should look for evidence that change our practice. So how might we catalyze the needed changes in university science teachers? Well, one way is to run workshops for college faculty to allow them to learn from expert colleagues how to incorporate inquiry into their teaching, what we call inquiry-based science education. And of course, we could also use the web to disseminate examples of outstanding teachers for others to build on. Just as we build as scientists on the science that other people have done, we should, in our education, build on the best science teaching that other people have done. So here I am at a workshop at the University of Wisconsin for college biology professors. This is since this time, 1,200 faculty have attended 10 years of these workshops. Here we're learning how to use clickers, which allow the students every 15 minutes to try to vote on the answers to a difficult question that the professor asks, that half of them will get wrong. After they do that, they then discuss with each other for 3 minutes in a very noisy, big lecture room what the answer might be, and then they vote again. And again, research shows that this is very effective in changing, even that small amount of activity is very effective in changing student performance, making them think and getting them involved in the material. That's just a very small change you could make, but there are many others, of course. There's a wonderful website called iBiology with many wonderful science talks, but it has a whole category about scientific teaching and presentations by some outstanding science teachers about how they've been able to change their science teaching to more active forms of learning in a variety of many different ways. So there's also many open access resources on the web for college science education. A wonderful fact about the internet, it allows us to freely exchange across the world all kinds of science resources. When I was editor-in-chief of Science Magazine, we had 2 years of contests for the best inquiry lab modules for college. And we published 24 winners of this prize. This was the first one we published. This is a physics course for college students, but we published 24 of them in many different types of science. In addition, we had another 2 years of contests for the best free science education websites. In each case, we published short articles about the winners, and also for the course materials for all those college courses were put on the web as a appendix, electronic appendix, to allow anybody to teach that course, sharing science education the same way we share science. And after I left science, as I was leaving, my present was to put up all the materials we had worked on education on a free website. You don't have to subscribe to Science Magazine. And from this portal, open access website, you could get all the materials that Science Magazine produces on education, including all the contest winners. Okay. So the U.S. National Academy of Sciences has also worked very hard on science education and produced hundreds of science education books, and they are free for downloading from the web as PDFs. This is the website. There are now 4,000 books online. most of them are not about education. Maybe 200 of them are about education, but many subjects. This is widely used around the world. This is the first major report we did on science education when I was the president, was how people learn, brain-mind experience in school. A very successful publication asking, what has psychology learned about how people learn, and how can that be applied to our schools? And this has actually been the largest selling publication in the Academy's bookstore. Then later, after I had left, the Academy produced a framework for K-12 science education for the United States. It became the guide for the new U.S. Common Standards for Science Education. And the most important chapter, and best chapter in my opinion in that book, was the one called Scientific Practices, stressing the importance of science education teaching scientific practices. That is, asking good questions for science, developing and using models, analyzing and interpreting data, and so on. So this is not like that science education that I talked about where you memorize words. It's completely different. The aim is to enable you to function, not to be a scientist, but to, in your everyday life, function with some of the skills of scientists so you could be a more effective person and not be fooled. So we also, the Academy then published this book called Ready, Set, Science, about science for children. It has what kind of science should be taught. It has wonderful examples. I should stress that some of these books have been translated into Spanish, and more could be. The Academy is happy to have other language translations of its reports. This is an important book that was recently published for university professors. Reaching Students, What Research Says About Effective Instruction in Undergraduate Science and Engineering. And I know there are deans of universities here in Chile. In the United States, I recommend to deans that they buy this little paperback book and put it on the chair of all their science professors. Because the science professors will never go read the web, but if you give them a book, maybe they'll, but it's very interesting because it has all these examples of professors who never wanted to change and then tried a little bit of change. And the basic lesson here is nobody can change their teaching at any level all at once. You have to start with a little experiment. Start with 2 weeks of active learning in your college class, and then the next year you could do more and some more. And it's the same thing at the lower levels. We cannot expect teachers to change their teaching suddenly. It's totally won't work. This is a journal published by the American Society of Cell Biology, open access journal publishing high quality science education and research about many, many different things. And I myself am very frustrated. I try to go to education journals and I have to pay $40 to get the article. It's terrible. But this one is free. So we have to make more education journals free. It's called Life Sciences Education. And it's a wonderful, and I'll show you, here's one of the articles. It's called Infusing Active Learning into Large Enrollment Biology Classes, 7 Strategies from the Simple to Complex, showing that active learning can easily be added to standard lecture classes based on all kinds of research that supports this kind of change in college teaching. So the good news is this new type of science education precisely fits the needs for workforce skills that have been widely expressed by business and industry. This is a a quote from a book published in 2002, which interviewed all these American companies, asking them what kind of skills they wanted for their high school graduates, people who were just getting entry-level jobs. They wanted a high capacity for abstract conceptual thinking, the ability to apply that capacity for abstract thought to complex real-world problems, and this is important, including problems that involve the use of scientific and technical knowledge that are non-standard, full of ambiguities, and have more than one right answer. Getting people to deal with a world where there's more than one right answer is an important part of science education. And finally, of course, the capacity to function effectively in an environment which communication skills are vital in work groups. Well, that's what you do if you're doing the kind of education I showed you pictures of, those 12-year-olds and the college students, the same thing. So this kind of science teaching also matches the forward-looking framework for the PISA science exam. And I just learned that Wynne Harden was the head of the original group that organized this framework. And the PISA assessment given to all 15-year-olds looks for people who understand the characteristic features of science as a form of human knowledge and inquiry, and students who can engage in science-related issues with the ideas of science as a reflective citizen. So just imagine a science education where you've memorized endoplasmic reticulum, Golgi apparatus, has nothing to do with this, has no effect on your really understanding important things. And so this exam has been a very important driver for improvements in science education around the world. Now, why does everything depend on scientists getting involved? And this is what I said at the very beginning. It won't happen without scientists. First of all, it's much easier to teach science poorly as the memorization of science facts than to teach science well. And without, if I'm a chemist initially, so in chemistry we have free energy, right? So everything that decays to a free energy minimum. And without continual input of outside energy from scientists, school science will tend to decay to the easiest thing to teach, which is memorize endoplasmic reticulum and then spit it back on an exam. So this is why we need scientists involved. Also, most current teachers, at least in the United States, are uncomfortable when students ask science questions for which the teacher doesn't know the answer. But we don't want the teacher to know the answer. Kids need to learn that we have to find the answers, and the teacher doesn't know everything. Nobody knows everything. So we need to change teachers, help scientists help change teachers to be comfortable with saying, I don't know the answer, but we'll find out the answer. And finally, a stable and consistent external scientific community is needed to support both schools and school systems for the many years, takes many, many years to create outstanding school science education. It's just critical, the force of outside scientists paying attention and being involved. So I'm just going to talk about a few examples, the amazing power of local science education partnerships. We've had a science education partner at my university in San Francisco for 25 years. Scientists are urgently needed to support teachers, and moreover, surprise, scientists have a great deal to learn from outstanding teachers of children 5 to 18-year-olds that will improve our own teaching. They learned that lecturing is not going to work very well. Well, this is my university, UCSF. Those red dots, that's a map of San Francisco, and the red dots are all the schools that have scientist volunteers active, more than 250 volunteers. Most of the volunteers are students, and they contribute more than 10,000 hours every year to interacting with students. And when scientists partner with teachers, they also discover how poorly most school systems are run. this is my latest frustration. This is a quote from a former principal, a friend of mine in San Francisco. They come to realize that, quote, experienced, effective teachers are a vastly underutilized research and education systems, perhaps the only resource that can truly create the change and improvements that students and teachers deserve. This is true for science education, but it's true for all of education, not only science education. School systems are the only thing in the United States that still run top-down. New boss comes in, superintendent of schools. They have a new plan that's going to fix everything in 2 years, and they last about, the superintendent turns over in about 3 years. So it's chaos. We need a different way, a smarter way to run our school system. So my latest editorial on science in Science Magazine is called Empowering Great Teachers. The only way I think that we are going to really make great school systems. So I say now is the time to create a national movement that empowers our teachers, and this is going to be difficult, but important. So this is last about the international cooperation. This picture shows a unchanged Jorge Allende. He doesn't age at all. He wrote a wonderful editorial about activities active in education, that movement of the World Academies that is represented at this conference. So the question really for us is, how can we best work together to spread good science education around the globe? And as I emphasized, it's going to require a lot of efforts from scientists. Well, we've already started. This is, again, Win Harlan had a major effect here, but it was a group. Rosa's here from Chile. Pierre Lina's here. Who else is here? This is a group of people. Guillermo Fernandez is here. So people from China to Chile to France, England, everywhere. Anyway, working with big ideas in science education, producing shared resources in multiple languages. So outstanding free resources for teaching are now available on the internet that can be carefully selected, translated, and adapted for use in other nations. And I'm just asking whether this could form the basis for a new project for the IAP partnership. I'm going to just show you two examples that I happen to know about. This is a wonderful article called Growing Seeds in Scientists. It's about a 5-year-old class working with seeds, just like the example I showed you, but it has a new idea, a new powerful, I think it's a very powerful idea. It introduces the idea of explicitly modeling a scientists' conference in class discussion. So in this class of 5-year-olds, the teachers first tried to explain how scientists have a conference, how they listen to people's ideas, how they're respectful of other ideas. And so these 5-year-olds are trying to explicitly model scientist behavior. I think this is a wonderful idea because it introduces what science is and how scientists use evidence for statements. Anyway, this article's pretty accessible on the web. That's there's some wonderful ideas out here. Here's a second tool. There's something called the Strategic Education Research Partnership that's spun out of the Academy. And they've been working in school systems to ask, how can we tell whether somebody's teaching well or not? How could the principal who knows nothing about science education walk into a classroom and see is this a good science class or not? So they designed a 5x8 card, a little card like this, for the principal or for anybody observing the class, with simple questions that they could look for without even knowing anything about science. The principal will see what kind of science is being taught. For example, are all students participating, that is, boys and girls? Do students say a second sentence? That is, there's classes where a teacher asks a question and a student says an answer. That's not a discussion. How often does a student say a second sentence? Thirdly, are students talking about each other's thinking? Not just the teacher. Are they talking about what Joe said or what Betty said in class? And are students revising their thinking and their written work after having a discussion? So these are kind of tools that could be used anywhere. And they were developed because the Strategic Education Partnership actually tries to work in schools, in real schools, and they realized the principals couldn't tell the difference between good and bad classes in all different subjects is impossible. They have to know everything. So there are tools like this that could be used and shared around the world. I'm just giving you examples of what I happen to know. People in the audience could come up with 100 more, but could the Interacademy Partnership spread these selected good ideas? So this is my last slide. Why are we doing all this? Why do we care? I'm not trying to produce more scientists. I'm trying to produce a better world. And there was a wonderful book written by a physicist, Jacob Bronowski, in 1956 called Science and Human Values. It's still in print. Now, Bronowski was a young man in the British Army, and he flew over Hiroshima and Nagasaki shortly after the atomic bomb had been dropped. And it greatly depressed him. It made him think that science could be bad for the world because it helped. Only with science could we make these horrible weapons. And he spent the next 10 years writing and reading and thinking about science. And of course, he concluded, on balance, science had been very good for the world. He said, "The Society of Scientists is simple because it has a directing purpose to explore the truth. Nevertheless, it has to solve the problem of every society, which is to find a compromise between the individual and the group. It must encourage the single scientist to be independent and the body of scientists to be tolerant. From these basic conditions, which form the prime values, there follows step by step a range of values: dissent, freedom of thought and speech, justice, honor, human dignity, and self-respect. Science has humanized our values. Men have asked for freedom, justice, and respect, precisely as the scientific spirit has spread among them." Thank you.